Hello everyone, my name is Mohit Gupta and you are watching CAM Fundamentals. In today's video, we are going to discuss HSAB Principle. This is part 6 of acid-base equilibria. The rest of the parts are given in the description box as well as in the I button over here. And most importantly, the link for the PDF of this lecture is available in the description box. So go and download it. So without further delay, let's get started. So today we'll start with the old concept. Before Pearson, there were three scientists, Ahrland, Chatt, and Davies, who divided Lewis acid and bases into two categories in 1958. The two classes were Class A and Class B. In Class A, all those metal ions that prefer to form complex with nitrogen, oxygen, and fluorine were considered in Class A, that form stable complexes with these ligands. Whereas in Class B, all those metal ions which prefer to form stable complexes with the ligands of the same group as that of nitrogen, oxygen, fluorine, but not with them. So, with phosphorus, arsenic, antimony, sulfur, selenium, beryllium, chlorine, bromine, iodine. So, any of the metal ion that form more stable complexes with them, they are considered in class B. So, in class A, all the S block elements, for example, alkali metals and alkaline earth metals, are considered in class A. Along with that, higher oxidation state 3D elements are also considered in class A. Whereas in class B, 3D elements, 3D transition series with lower oxidation state, along with that, heavier transition elements are considered in class B. So let's talk about the Pearson concept. So this is the image of Pearsons, and if you want to know more about him, you can go through following link. So he classified those two classes, class A and class B, into hard and soft acid bases. Along with that, he also introduced a borderline category of acid and bases that show characteristic feature of intermediate between hard and soft category. They don't fit in the hard category and they also don't fit in the soft category. So these two categories were divided on the basis of polarizing power as well as on the polarizability. So first let us discuss what is polarizing power. So it is the ability of a cation to attract electron cloud of an anion towards itself, which means if there is a cation and if there is an anion and they are forming a bond, so the cation will try to polarize the anion and it will attract its electron pair or electron density towards itself. So the polarizing power is directly proportional to the charge and inversely proportional to the size, which means if we have a small size cation, it would have high polarizing power, and if the cation have higher charge, then it would also have higher polarizing power. So small size, large polarizing power, and higher charge means larger polarizing power. On the other hand, polarizability is the ability of anion to get polarized. So if it has a lot of charge and its size is very large, then it can be easily polarized by a cation. So polarizability of an anion is directly proportional to the charge. Moreover, it is also directly proportional to the size, unlike the polarizing power. In this case, if the size of the anion is large, which means it has larger polarizability, it can get polarized very easily, and it also has higher negative charge, then obviously its size would be very large and in turn it would have larger polarizability. So let's talk about the Lewis acid first. So we'll be categorizing it into the hard acids, soft acids, and in the borderline. So these are divided on the basis of the polarizing power. So in case of hard acid, we have the cations having very high polarizing power. And if a cation have high polarizing power, which means it has smaller size and it would have higher positive charge. On the other hand, in case of soft acid, the polarizing power is less, which means the sides need to be large and the positive charge need to be minimum, 0 or low positive charge. So all the light metals, like all the elements of the S block, alkali metal as well as alkaline earth metal, are considered in the hard acid category, whereas other heavy metal ions are considered in the soft acid. Light means they have low atomic mass and heavy means they have higher atomic mass. So in case of hard acid, they have fewer d electrons, whereas they have nearly filled d orbital electrons, which means we are talking about the transition elements of very high atomic mass. Moreover, they are highly electropositive and they are less electropositive. So let's talk about some examples. In this case, we know S block elements like H plus, Li plus, Na plus, K plus, all of them are considered in hard acid. So in this case, we have aluminium 3 plus, where the size of aluminium 3 plus is very small, even smaller than magnesium 2 plus ion. So it is also considered in hard acid. Along with that, D block elements which have very high positive charge are also considered here. P block elements having very high charge like chlorine plus 7 is also considered here. In terms of Lewis acid like AlCl3, BCl3, so AlCl3 and BCl3 are considered in the hard acid, whereas the higher member of this group are considered in the soft acid. So let's talk about the soft acid first. In this case, we have transition elements which have nearly filled d orbital with low charge like copper plus, Ag plus, Au plus. They all are considered in the soft acid. Along with that, AlCl3 was written here, then GaCl3, GiI3, InCl3, all the Lewis acid of the same group with higher atomic mass are considered in this soft acid. I plus Br plus are also considered in the soft acid because they have very large size and low polarizing power. Moreover, metal atoms that do not have any charge are considered in the soft acid category. And the borderline are Fe2 plus, CO2 plus. So Fe2 plus is here and Fe3 plus is here. Cobalt 2 plus is on the borderline and cobalt 3 plus is on the hard side. Nickel 2 plus, Cu2 plus, zinc 2 plus, Pb2 plus, Sn2 plus, Sb3 plus. So these are the P block elements. They are also considered in the borderline category. Okay. So let's move to the Lewis basis, the donor or the ligands. So in this cases, the category was divided on the basis of the polarizability. So hard bases have low polarizability, that means it has small size, high electronegativity, and moreover they also have filled orbitals. Soft bases on the other hand have low polarizability, which means they have higher negative charge, larger size, and hence have low electronegativity. They generally have partially filled orbitals, and those which cannot be categorized in the two categories are considered in the borderline. So in case of hard bases, oxygen, nitrogen, and halogen, especially fluoride and chlorides, are considered in the hard base. However, carbon ligands such as carbonate and oxalates are the two exceptions. Along with that, we have two more exceptions, sulfate and phosphate. So these four are the exceptions: phosphate, sulfate, carbonate, and oxalate. In all of these elements, the central atom has very high oxidation state. So remember that. In case of soft bases, the sulfur ligands are considered here, the phosphorus and arsenic ligands are considered here. After fluoride, chloride, all the bromide, iodides, they are considered here. All the carbon ligands are also considered over here. So it's very simple with the four exceptional cases. Moreover, the several nitrogen ligands are also considered in the borderline, like aniline, nitrate, nitrite, pyridine. They all are considered in the borderline. So let's talk about HSAB principles. HSAB stands for hard soft acid base principle, and sometimes it is also pronounced as SHAB principle, soft hard acid base. So according to the HSAB principle, hard acid always prefer to combine with hard base. Only then we'll be able to get a stable product. Or soft acid prefer to combine with the soft base and then it is able to provide a stable product. So if you want a stable product, so you should have hard acid and hard base, or the combination of soft acid and soft base. One more variation of this HSAB principle is larger cation stabilizes larger anion and smaller cation stabilizes smaller anion. So if you have smaller cation, it is hard, and smaller anion means it is also hard. Larger cation means it's a soft cation and larger anion means it's a soft base. Okay, so it's another variation. You can use this concept also. So bonding between hard acid and hard bases occur through ionic bond. So if you have smaller cation and smaller anion, that is, if you have hard acid and hard base, then the electrostatic force between the two would be very high and that compound would be ionic. For example, Mg2 plus and OH negative, the oxygen donor, that means it's a hard acid, and the Mg2 plus, it's a alkaline earth metal, it is also hard acid. So they form an ionic bond. Okay, bonding between soft acid and soft base occur through a covalent bond. Since they have very large size and low charges, therefore they prefer to form covalent bond. For example, HgI2 forms a covalent bond where Hg2 plus is a soft acid and I negative is a soft base. So next we talk about the applications of HSAB principle. So first application is we are able to predict the stability of complex. So for example, AgI2 negative is more stable than AgF2. Obviously, the Ag is soft acid, F negative is a hard base and I negative is a soft base. So soft acid prefer to form a bond with soft base. Only then we'll be able to get a stable product. So AgI2 negative would be more stable than AgF2, which is formed between the soft acid and a hard base. Similarly, COF6 minus 3 is more stable than COI6 minus 3. Why? Because cobalt in 3 plus oxidation state is a hard acid, whereas cobalt in plus 2 oxidation state is a borderline. Okay, remember that. So in that case, a hard acid prefer to form a bond with hard base and then the product form is more stable. In this case, we have hard acid and a soft base. The next is linkage of ambidentate ligands to the metal ion. So first of all, let us discuss what is ambidentate ligands. So ambidentate ligands are the ligands or the Lewis bases that have two or more donor atoms, but they prefer to donate from only one at a time, which means there is a molecule which has two or more donating sites, which means it has two or more atoms which can act as a Lewis base, but they don't attack simultaneously at one time. Only one is able to donate. For example, SCN negative. In this case, sulfur and nitrogen both are capable of donating electrons, and hence it has two donor atoms. Sulfur is a soft base whereas nitrogen is hard base. So on the basis of the sulfur and nitrogen, their hard and soft nature, we can easily predict which kind of bond will they form. So in this case, we can predict which atom will combine to the metal ion. So if we have a metal ion which is hard in nature, obviously nitrogen will going to form a bond. And if we have a metal ion which is soft in nature, then sulfur would prefer to form a bond. So in this case, we have Pd2 plus, which is obviously a soft acid because it is a transition element with lower oxidation state and more d orbitals, which means it's a soft acid. So in this case, SCN negative will prefer to bond from the sulfur side because it's a softer one. Okay, so in the case of chromium 3 plus, which is a hard acid, nitrogen will prefer to form a bond and we'll get this kind of product. Let's take one more example. In this case, we have nitrogen as well as phosphorus. So in this case, we have BF3. Now BF3 is a hard acid, so it will prefer to form a bond with the hard base, so it will prefer to form a coordinate bond with nitrogen. Similarly, if we have BH3, which is a soft acid, this is not a hard acid. Hard acid is BF3 because three fluorine atoms are attached to it, making the boron very much electron deficient. In this case, BH3 is a soft acid, so it will prefer to form a bond with a soft base like this. Here remember that boron is in +3 oxidation state and hydrogen is having -1 oxidation state. So it's a hydride, boron hydride. The next important property is symbiosis, or sometimes also called as symbiotic effect, according to which hard base prefer to attach with that atom which is already having hard ligands. So if you have a hard base, it will prefer to attach with a atom which is already having a hard ligands. We'll get to know more about it with examples. Moreover, soft base prefer to attach with one atom or that atom which already having a soft ligands. So in this case, we have all these fluorine atom which are hard ligands. So nitrogen will prefer to form a bond with one atom which is already having bond with the hard ligand. So nitrogen will prefer to form a bond with boron which is already having hard ligands attached to it. Now In this case, we have BH3 and we have hydride. So hydride, being a soft base, will prefer to form a bond with boron, which is already having bonds with hydride ion, which are also soft ligands. So these are the soft ligands and this is the soft base. Now let's consider this. You have BF3 and you have NH3 and hydride ion. So in these two cases, which will prefer to form with bond with BF3? Obviously NH3. And in this case, if you have BH3 and you have H negative and NH3, which will prefer to form bond? This hydride ion as compared to the NH3. Why? Because of this symbiotic effect. One thing you need to know, these three hydrogen are present as H negative, not H positive. So they are not protons, they are hydride ions. And H positive is a hard acid, whereas H negative is a soft base. You need to remember that. So let's talk about one more example. In this case, we have CO cobalt ion, which is attached to Cn negative cyanide ions, and they all are soft ligands. So in this case, we have SCN negative, which is a ambidentate ligand. Now, cobalt already having soft ligand, so a softer base would prefer to attack and will get this complex. However, if we have CONH36, in this case, all the ligands are hard. So if I'll add a ambidentate ligand, nitrogen will prefer to attack. Why? Because it is already having hard ligands. So this is also in agreement to the symbiotic effect. Now let's talk about the solubility of the compounds. In this case, we can also predict the solubility of the compound depending upon the ionic and covalent nature or the stability of the compound. For example, in this case, I have lithium iodide, which is more soluble in water than AgI. Why? Because lithium iodide is more ionic than AgI, where AgI is covalent and LiI is ionic. Why so? Because lithium positive is a hard acid, whereas I negative is a soft base. So we know hard acid when combined with hard base, it forms ionic bond. Soft acid when combined with soft base, it forms covalent bond. However, we have hard and soft, which means it is a polar covalent bond, but since it is still polar, it is soluble in water. So this is more ionic, readily dissolves in water. Whereas AgI, in which Ag plus is a soft acid and I negative is a soft base, since both are soft, so that means they will form a covalent bond, and since the bond is covalent, it won't be able to dissolve in water. Or we can also say soft acid combined with soft base to give stable product. So since it is more stable, it won't dissolve in water. The next example is HgOH twice, which dissolves readily in acidic solution, whereas HgS doesn't. So in this case, we have Hg positive, which is a soft acid. Why it is soft? Because it is D block element. Moreover, it has lower oxidation state. Along with that, it has more number of D electrons. OH negative is a hard base because it has oxygen donor atom. So if they form a compound, it would be less stable and it will readily dissociate or dissolve. On the other hand, HGS is formed between the soft acid and soft base, a more stable compound, which means it is difficult to dissolve or dissociate. The next example or the next application is of occurrence of metal in nature. So HSAB principle is capable of justifying why some elements exist as oxides in carbonate, whereas some elements exist in nature as sulfides. So magnesium, aluminium and calcium, Mg2 plus, Al3 plus and Ca2 plus, all are hard acids. So they prefer to form a bond with oxide or carbonate and not with the sulfide, which are softer in nature. Similarly, copper plus, Ag plus and Hg2 plus, they occur in nature in the form of sulfides. Why? Because sulfides are soft bases and they all are softer in nature. So soft acid prefer to form a bond with soft base. On combination, they will form a stable compound. That's why they occur in nature. And they don't prefer oxide and carbonate to form bonds. The next application is the course of the reaction. So if you have a double displacement reaction, you can easily find out whether the reaction is going to happen or not. So let's take an example here. You have lithium iodide and cesium fluoride. When you combine with them, you will instantly get lithium fluoride and cesium iodide. Why? because in the product we can see we have hard acid and hard bases, soft acid and soft base. So the product are more stable as compared to the reactants which is formed between the hard acid soft base and soft acid and hard base respectively. Similarly, BeI2 on reaction with HgF2 prefer to form BeF2 and HgI2. So you can easily find out whether a reaction would occur or not. If the product are stable, it will go in the forward direction. If they are not stable, the reaction won't occur. The next application is the stability of the complex. So obviously on the basis of the hard acid soft bases agreement, you can easily find out whether a complex is stable or not. Compounds or the complexes having all the ligands of the same nature are more stable, whereas compounds or complex having ligand with mixed nature are less stable or unstable. Here nitrogen and fluorine both are hard ligands, so all the ligands are hard, therefore it is more stable as compared to cobalt NH3 5I which have hard and soft combination. So if all the ligands are of same nature, either hard or soft, that complex would be more stable or less labile. Here in this case we have COCN5I, so this is soft and this is also soft, so this complex is more stable than COCN5F2 positive where CN are soft bases and F is hard base. The next application is site preference. So on the basis of hard and soft sites, we can easily predict which nucleophile or which electrophile is going to attack. For example, I have taken alpha beta unsaturated ketone. So this is ketone C double bond O, and on its alpha and beta position we have one unsaturation. Therefore, we call it as alpha beta unsaturated compound. In this compound, we have C double bond O, which means it's a hard site, and whereas in this case, since the bond is between carbon and carbon, obviously it has to be categorized into the softer side. Okay, so organocuprates, so organic compound having cuprates, that means it is bonded with the copper, and thiols, which means sulfur is attached to it. So both of them will prefer to attack on the softer side, whereas organolithium, lithium is present, Grignard reagent which is RMgX, magnesium reagent, so both are hard acids, so they will prefer to attack on the harder side. So let's take an example, RuCuLi, this is your Gilman reagent. In this case, R will attack on this position to form 1,4 addition product. Whereas in the case of RMgX, the R negative would attach on the harder side and we'll get R here and OH on the hydrolysis. So we'll get 1,2 addition product. So it is on the basis of this hard and soft nature, we can easily predict whether we're going to have 1,4 addition product or 1,2 addition product. So let's talk about the limitation of HSAB principle. So first of all, it is unable to explain several reactions. So a lot of reactions are there which HSAB principle is unable to explain. One example is here. We have SO3 2 negative which is a softer base and SO4 2 negative is a hard base, remember. So SO3 2 negative is a soft base, and when it react with the HF which is formed between hard acid and hard base, it form HSO3 negative hard acid soft base plus F negative. So on the basis of HSAB principle, this reaction won't occur. However, this reaction proceeds in the forward direction. So this HSAB principle is unable to explain this observation. Along with that, it is unable to explain the relative strengths of the acid and bases. So we might have lot of hard acids and we might have lot of soft acid and bases, but we are unable to predict which one is stronger and which one is less strong. Moreover, H plus is a hard acid and H negative is a soft base. So the bond between hard acid and soft base should be polar covalent. The bond between hard acid and hard base is always ionic. The bond between soft acid and soft base is always covalent. But the bond between hard acid and soft base is always polar covalent. However, the bond formed between the H2, the two hydrogen atom, is always purely covalent. So this is also a weird observation which cannot be explained on the basis of HSAB principle. So this is it for the today's video. If you like the video, then please hit the like button and please consider subscribing. If you want to go through the playlist of this series, then go for this. And if you want to refresh or revise the last video, you can. click here. So this is Mohit Gupta signing off. Have a great day.